Good afternoon, everyone, and welcome to today's webinar. My name is Richard Martin, one of the product management team from Electro Rent. I will be your moderator for today's event. The subject for this session is building a robust 5G network, focusing on the backhaul side of this network evolution. Let me introduce today's speaker, Roland Stuss, who works for Viavi Solutions as an expert field applications engineer. He will be taking you through today's topic. Should you have any questions about any of the items raised in today's session, can I please ask that you put them into the chat section of the tool, and we will answer them as best we can at the end of our session in our Q&A section. With the formalities out of the way, I'll hand you over to Roland and he can take you through this webinar. Roland, over to you.
Yeah, thank you, Richard. And also welcome to everybody on that webinar. And yeah, let's start. About the agenda of today. Okay, the topic is backhaul, but also we'll talk about CPRIO to eCPRIO evolution. This is actually Fronthaul, but it's transport, and we are talking about transport testing, and therefore it's part of the seminar of today. Then also we'll talk about synchronization. What is synchronization? How is it done in 5G, and why is it needed? And then quality of service. I will not talk about let's say classical quality of service. Quality of service is still since a long time in the transport, telecom, datacom networks. I will focus on enhancement on the classical quality of service needed for time-sensitive networking, because this is also an important part within 5G deployment. Then I come to the backhaul transport testing and troubleshooting. And at the end, a few words about fiber end phase inspection, because everything is fiber, and it's very important that the fibers are clean before you make the installation or the connections. And of course, I'm talking about a lot of technology, functions and features, and therefore at the end I want to give you in one slide a quick overview. What are the Viavi testers for that technologies I've shown and explained during the webinar. If you heard about Viavi, maybe you heard the name the first time, company Viavi. It's actually 5-6 years on the market. The name, it's actually the name, but the history is quite long. It's as you see on that slide, I will not go through all of them. It's in the meantime a summary of a lot of different company parts come together by merger or by acquisition. And yeah, the first company was Wandling Golderman, a German company, and yeah, it's 1923, so we are close to 100 years of experience, expertise in that company, Viavi. First part now, CPRIO to eCPRIO evolution. Mobile access network. Yeah, at the beginning we have this big boxes, the base station. It was with a copper cable, it's more a tube to the antenna. This was the first installation, and then later on the next step was that the base station became separate to a baseband unit and a remote radio unit, and the connection now it's fiber. And as we have here fiber, we need a transport technology to carry this encoded RF signal to the radio unit, and this is then done by CPRIO protocol. It's called TDM-based, slot-based protocol to carry this data. And with this separation in remote radio unit and baseband unit, we got now the Fronthaul area. With the CPRIO and this fiber connection between baseband unit and remote radio unit, we have the big advantage because it can be much longer as before with the copper tube. And this also allows to place all these baseband units in one building, and the so-called baseband hotel. So even it was possible, instead of using only direct fibers, to use DWDM system, to have one fiber go to the area where we want to have the radio units, where we have our cell sites. So this is then this so-called distributed antenna system. So however, with a fiber you can cover long distances, but with the CPRIO protocol and allowed delays. The maximum delay between the baseband unit and the radio unit is 100 microseconds. This is around 20 kilometers. So it's quite a large area, but yeah, it's a limitation. And if it comes down to 5G, CPRIO doesn't scale the 5G requirements. 5G, yeah, when we go to this massive MIMO and this massive MIMO antenna elements, so 64 TX RX elements, when we take the CPRIO technology, transport technology, this will mean that we have to take here an interface with a capacity of 100 gigabit. It's not really economical to have here 100 gig interface, to have here 100 gig interface. Therefore, another step of evolution is needed when we're coming to 5G. And the next step is that this direct fiber connection, so the baseband unit is now called centralized unit. We have the radio units. In between, we have this cloud. It's a packet-based network to carry these encoded radio signals from the CU to the RU. And yeah, it's no more a direct connected fiber between the CU and the RU. It's a packet-based network, and you organize here inside these logical connections from the CU to the different RUs. So the CU can control now a number of radio units, not only one. And another change is that the centralized unit is now further split into centralized and distributed unit. And then we have our radio units. Now you see we have another hall, it's now the mid-hall. We have the front hall, the mid-hall, the back hall. And the centralized unit, quite a big device from its function, can control now a number of distributed units, and the distributed unit can control a number of radio units. So it is quite a aggregation mode, which helps to really cover this. A lot of new cell sites needed with 5G deployment. And the delay of 100 microseconds, this limitation which we have learned with CPRIO is still the same between the distributed unit and the radio unit. So the maximum delay is allowed to, one-way delay is allowed to be 100 microseconds. And eCPRIO protocol, or the eCPRIO technology, transport technology, is here between the distributed unit and the radio unit. Here in the mid-hall, it's, let's say, normal data transport, but here we have a specific eCPRIO protocol and eCPRIO transport technique. It's based on Ethernet, of course, but it's focused here on distributed unit and radio unit. Okay, about testing or how these logical connections are defined. If you have a transport network in general, you have always at the border of the transport network the user network interface where the devices are connected to. And in the eCPRIO terminology, we have the radio equipment controller and the radio equipment. This is the radio unit connected physically with Ethernet interface to the transport network, which is the Fronthaul. And you see on the left side, actually, radio equipment controller and radio equipment is one unit. It's the eNode B, but it's in separate boxes, in two boxes with a Fronthaul network in between. And the Fronthaul network is this packet-based transport network. Now we need this logical connection between these two. And this is organized with the Metro Ethernet formal specification for EVC, for Ethernet virtual connection. So this is how we interconnect radio equipment to the radio equipment controller. And here we are back in our traditional area with transport testing. So MEF specifies the EVC and of course also specifies performance attributes to qualify such a connection. If it's to qualify it and also to turn it up and to verify its proper operation. So it's frame loss ratio, it's frame delay, and it's frame delay variation. In eCPRIO, it's beside frame delay. Yeah, normally frame delay is in a round trip mode measured, round trip delay, but here it is also one-way delay because we need to check that the delay between controller and radio equipment is within the 100 microseconds. About testing in this area, I want to show you one example. And this one-way delay is part of the eCPRIO protocol. So it's not a separate function which can be done by a tester. It's implemented in the eCPRIO, and so it means in the communication between a distributor unit and a radio unit. So they can exchange this timing information to check if it's 100 microseconds more or less. And this is a screenshot from one of our test tools, and it supports this eCPRIO one-way delay measurement. And the nice and good advantage is, on one side, you have both results for each direction, so local to remote or remote to local. One is to verify, okay, how much is the total delay? Are we in this 100 microsecond accuracy or limitation? And of course, also, it can be used to basically verify the asymmetry of that network. About the asymmetry, this is important. This we will learn later on in the synchronization part, that asymmetry is a kind of killing factor for synchronization of 5G networks. And yeah, as we have implemented it like it is with a eCPRIO device, so we can do measurements like this. New cell site location, verify 100 microsecond and asymmetry against the DU. If you know that the DU is well synchronized in time, you can do it the other way around, or between two testers to verify the Fronthaul transport network. So this is all possible. So this is one part to verify this 100 microsecond and partially this asymmetric delay. A second step is to qualify and verify the services. So it's not only one-way delay, it's of course, eCPRIO has, in this example, 5 different service types to support between DU and RU. And most of the time they will have separate VLANs, or they are separate services, and we can qualify. At the same time, one-way delay measurement and qualification of the services, if they are within their SLAs. And the round trip time accuracy can be really in the sub of 2 nanoseconds. And the one-way delay, it's in a similar range. It can be from the accuracy 5-6 nanoseconds. So this is already possible. So this was about this evolution from CPRIO to eCPRIO, and eCPRIO is part of 5G network installation in the Fronthaul. Now coming to synchronization, what it means and why is it needed. On the table on the top, you see we have 2 radio technologies in the mobile world. We have this FDD, frequency division duplexing. And if you go more to the right, you see it requires only frequency synchronization, no time synchronization. Frequency synchronization means here we have the cell side, the radio unit. We have here on the right side and a mobile in the network, in the area there. And the communication is done on the RF interface with an uplink frequency and a downlink frequency. So 2 frequencies per direction. So per direction, the frequency. So no interference, no problem. And it's organized in this way that if there is another mobile, it has another uplink frequency and another downlink frequency. And all uplink frequencies are organized in the same frequency band, and the downlink also in the same frequency band. And in between, you have a guard band to make it really secure that there is no interference between these frequencies. You always need to know when you're here with the mobile, uplink, you have a strong signal. Downlink, you have a weak signal, and therefore a strong signal can interfere the weak signal. But if it's that well separated, no problem. Now, if it comes to 5G, we have this TDD. This is called now time division duplexing, and you see it requires more or less the same frequency synchronization accuracy, but also phase, or let's say time synchronization. This means all cell sites need to have the same absolute time with an accuracy of plus minus 1.5 microsecond on the RF side. Why is this needed? You see on that picture here, it's not only one frequency from the cell side to the mobile, and within that frequency we have a downstream and an upstream direction. So it's organized, it's called a 5G frame, and it's organized in slots for up and for downstream. So you switch in between the direction. If there is a second mobile, it has the same frame structure. It has at the same time down and upstream, so no problem. Let's assume there is a third mobile, and it starts here, this cell site starts a little bit earlier like the others, then we have here now a problem. Here we have a downstream and upstream at the same time, and this is interference. This is not allowed by EU regulation. There is a report which says to all operators, to all mobile operators, not only within one operator network, all network operators, even when you have 5G in a campus area, so let's say a private 5G network, everybody has to start this frame at the same time, and everybody has to have the same frame structure to avoid this interference situation. And this means every cell site needs to start at the right time. So every cell site needs to have the right absolute time to be able to start all frames, 5G frames at the same time. This is why we need this time synchronization in 5G at the radio unit. So how is this done, this synchronization? Explained now in a simple way. So we have frequency and time, transport and distribution. About frequency, this is called layer 1 physical method. It's only for frequency, and it's simply done. Here we have our reference oscillator, our reference frequency, our reference clock, and we have maybe a 10 gig Ethernet interface, and this 10 gig Ethernet has a TX clock here, TX clock, and the port here will take this receive clock and recover it, and will internally take this clock to tune its internal oscillator on that, and use now this oscillator to generate on the other side the TX clock for its 10 gig signal, or for its 100 gig signal, doesn't mind. So it goes now step by step, this frequency from the reference clock down or up to the, let's say here to the cell site, to the radio unit. Of course, this is also possible external reference frequencies used, but this is the idea. On the interface, on the used interface, you use the clock for frequency distribution and forwarding. But it's only frequency, and you know, we need now also absolute time here at the cell site. To get the absolute time to here, we take now the timing over packet mode. This is the precision timing protocol, PTP 1588. Timing over packet means we have now here also a reference time, and the master here, he takes this time and puts it into these frames and this Ethernet or PTP payload. And you see from the arrows, this is a bidirectional communication. So both are exchanging PTP messages with the goal that at the end, this cell site, the system time of this cell site is the same like here from the reference time of the reference source. This is the goal of PTP based on exchanging packets. How is this done, this PTP? How is it working? We have a master clock with its system time. We have a slave clock with its system time. And now it's the goal, of course, to tune this system time to the master time. The messages exchanged, one is the sync message. It's coming from the master. And the sync message includes in its payload the time, exactly the system time when the first bit of the sync message is going out of that port, of the master port. So when the first bit goes out, this time, the system time is then put into the payload of the sync message. And this is called timestamp number 1. The sync message goes over the network, received by the slave. And the slave takes now from its system time, when the first bit of the sync message is received, it looks to its system time and says, yes, it received at this time. And it says this is now time 2. Okay, he has now more or less a downstream delay, but he needs to know the round trip time, because the sync message timestamp is when it leaves here the message. But the slave needs to know the delay to the network, because this is a correction value. The network delay has to be added to the timestamp received in the sync message. Therefore, the slave in parallel starts a process. It's called delay request message. When it sends out, it remembers the time when it was sent out. The slave receives this delay request, remembers the time when it has received the first bit. It's timestamp 4, here it's timestamp 3. And this timestamp 4 is sent back in the delay response message to the slave. And at the end, if this process is true, the slave has 4 timestamps. And it can calculate now the mean pass delay. This is more or less the round trip time. T2 minus T1 is the downstream delay. T4 minus T3 is the upstream delay. Both together divided by 2 is the mean pass delay. Of course, at the beginning, this system time is completely away from the master system time, but this process, sync, delay, regress response, is continuously running, typically 16 times per second. So, and the slave always corrects its system time with the goal to have it somehow, the offset from its system time to the master time, 0. So this is what a slave is doing. Continuously exchanging these timestamps, continuously changing the system time until it says, yes, now my offset to the master time is 0. Then it assumes it is in sync with the master. But of course, if there's some asymmetry, delay in the network, it's wrong. It has a time error. But this is the basic process, how it's working. And back to the 5G, and there we have 2 time information which has to be of thresholds, let's say a time alignment and a time error, a time alignment error and a time error. So we know distribution unit can organize a number of radio units. Typically this is called a cluster. And all these radio units should have the same time. And the time alignment is the tolerance. What could be the offset between these radio units in absolute time? From the specification, it's called, it has to be in one cluster, but in the meantime, the experience is that this time alignment limitation should be over the whole network, not only over the clusters, over the whole network. And this time alignment thresholds are, if you have your normal RF function, though it's about below 3 microseconds. Once we start, 5G on the other side has a lot of advantages. Carrier bonding, MIMO, beamforming. If you go to the maximum beamforming and carrier bonding, the requirement is 60 nanoseconds time alignment, below 60 nanoseconds. So this is the time alignment, and it is measured on the RF side. The time error is now here measured on the user network interface, on this Ethernet interface, and the time error says, okay, how much is this radio unit away from the big reference time? So maybe we have somewhere in the core, in the backhaul, satellite a reference clock using the satellite, GPS, Galileo as a reference time, and then with PTP protocol forward this time to the different radio units. So this is the time error. And the time error is in the range of below 1.1 microseconds. So here we should have a maximum error of 1.1 microseconds. So if the network introduces here 1.1 microsecond, let's say plus, then the radio unit is 1.1 microseconds away from the reference time. Okay, but nowadays we don't have only one big master to control all the radio units or to distribute from there all to the radio units with PTP, the time. So in the Fronthaul, North or maybe Mid-Haul area, there is the ORAN, and they are discussing now, okay, like these 4 different examples. This PRTC means now it's a GPS receiver, or GNSS receiver, satellite receiver, with getting the reference time from the satellites and then feed a PTP grandmaster. And this grandmaster via PTP will give then the time to the slave, to the radio unit. So the master can be in a distributed unit and only the Fronthaul network, native switches, very risky. Or we have the situation that we have these boundary clocks into between. Boundary clocks are switches with an additional function, PTP aware, to have a better performance in forwarding this PTP via PTP, the reference time to the slave. Or we have a situation that there is an operator in that Fronthaul area as a sub-operator for the mobile operator. he has a satellite receiver, he has a grandmaster, and with this grandmaster, he forwards the PTP timing to his boundary clock, and from there to the distributed unit of the operator and to the radio unit. Or we have already at the radio unit a GPS receiver. So now when you're a little bit familiar with synchronization, I think, hey, if we have these situations, we have 4 different sources of reference. This is not good, this will not work. No, we have only one reference. Our one reference is the satellite system. And this is only a connection to the satellite system. Of course, there will be a little bit of difference, depends on the used satellite receiver and the performance of the satellite receiver, but we are still in the tolerance that we can do that situation. This means we have no reference time somewhere in the backhaul. It's all in the fronthaul area. Okay, this was all about synchronization. And next step is now coming to transport measurements in the backhaul. I've also added here quick information about functional split and network slicing. So this is often mixed up, or somebody thinks it's the same. I want to show the difference. And then also this quality of service enhancement for this time-sensitive networking, what it means, and exactly what it means. Functional split and network slicing. Functional split means we are here in the fronthaul, mid-haul area, centralized unit, distributed unit, and radio unit. And these blocks here with the short forms, these are all the protocol, the whole protocol stack needed to get the user data encoded in the packets that the radio unit can make the right frequency and add the right data for that mobile, which is at the moment here using, let's say, web browsing in the internet. And these protocol parts can now be put into one of these 3 units, depending where you put it in. So this is called net functional split. So this is a function. These 5 functions now in the distributed unit, these 2 in the centralized, and these 2 in the radio unit. And here we have a split. There are different split profiles, and it depends on what is the mobile operator achieving in that area. Can be more in the radio unit, can be more in the centralized unit, or let's say this example. This is functional split. This is completely in the mid-haul fronthaul area. Network slicing. This can be over the whole network. We have a whole network infrastructure. And over the infrastructure, of course, we transport and carry all the data for the different applications and services. And therefore we have to split this network. These are, for example, of services. Now we have to, not to split, we have to slice this infrastructure into, in my example here, 4 different virtual networks. And each of these slices has to need a special performance depending on the service. So in the mobile 5G environment, we are talking about these 3 typical applications. Enhanced mobile broadband. This is here. This means bandwidth, bandwidth, bandwidth. Not only 200-300 megabit download speed, and we are talking about a number of gigabit download and upload speed for our portables, for our mobiles, where we are in this 5G. We want to have a lot of bandwidth. The other thing is this massive machine type communication, Internet of Things. Every device, every sensor, every switch is now in the internet in the future, and it wants to communicate. It's connected to 5G. It's not a lot of data, but a lot of devices which have to be controlled. And this is the challenging service, ultra reliable, really extremely reliable, and low latency communication. This can be in that connected cars, autonomous car driving. This is then here that we need here a very reliable service and very short delays. And maybe also with manufacturing. So the robots are here at that side, and somewhere in the cloud is, let's say, the software, the program controlling the robot, and this requires reliable and very short delay communication. I have another example, maybe a funny one, but who knows, this can happen in the future. Let's assume we have a hospital, they're the operating room, and now there is a operation on the heart from a person, and the heart specialist at the moment is at home, not in the operation room. And they need now the help of this heart specialist. So they call him, and the operation is already supported by a roboter. So the surgeon will take his mobile joystick device and then control from there the roboter in the operation room. So sounds funny, but it's mentioned that this can happen in the future. And I guess we all agree that this requires a very reliable connection and a very low latency communication. So these are these applications we will have in the future. This is for the moment a little bit not yet available with 5G implementation, but in 2-3 years, probably it will be a service available in 5G. Good. About TSN. So this is needed for successful deployment of 5G. Yes, we know that, what 5G wants to deliver. And especially this ultra-reliable, low-latency service. This requires extreme enhancement in the transport network. This TSN quality, time-sensitive networking. And should be done on a single transport technology. So we have now switches, routers in the network. And with classical quality of service, so queuing, prioritization, policing, shaping. But this is all store and forward. You can prioritize as much as you want. You will not achieve the requirements of TSN network functionality. Therefore, it needs enhancement. And IEEE already specified standards for these enhancements. And I will show now in one slide what is, let's say, the maximum possible solution of these enhancements. So in my example here, I have 3 switches. And they have to support store and forward. This is the classical way. Receiver frame, look to the destination address, switch it internally to the external port, to the access port, and then send it out. This is store and forward. But to reach this TSN performance, we need cut-through mode. What means cut-through mode? If a frame is received, the switch looks to the destination address. Once it knows the destination address, it immediately forwards this frame to the egress port. And here you have to open the gate for the egress port. So the egress port needs now to be available for this frame, and not for any other frame. So it's a high priority function. So it has to be available, the egress port, when the frame is received. And we have now a number of switches. All switches should open this egress gate at the same time. Otherwise, it will not work. So we need this scheduled priority queues. You see here this block scheduler beside the queuing mechanism, the queuing configuration. We also need a scheduler controlling these queues. So we have normal queues, but we have high priority queues, and we have this cut-through queue. And that is possible. We need a time synchronization. These switches need to have a system time synchronized. All have to have the same time, that all open at the same time when the scheduler says, now it's time to open the gate. They have to open the gate and the frame will go through. Okay, this needs a protocol to configure the scheduler. This is a reservation protocol, because let's say in our example with this heart specialist, it's only needed for half an hour. So stream reservation for half an hour, we need here now this special service for this TSN service. So this is now like a line-oriented wired connection, extremely fast through the network. No store and forward delay. And if we have here boundary clocks, if we have here organizing already with boundary clocks, the PTP distribution, they already have the time, so we need to add the scheduler and of course this function of cut through. Good. Now coming to turn-up testing and troubleshooting with 5G backhaul. And I have to say, when I've been asked to provide a presentation about 5G backhaul testing, actually, it's still the same. The story is still the same. However, with 5G, new services with special performance requirements, ultra low latency, new interface rates. You will see 5G requires quickly 100, 400 gig interfaces capacity, enhanced transport techniques, TSN, this cut-through switching, new physical link qualification. We will learn more about it in 2-3 slides later. And the basic story about testing is still the same. If you construct a new network, you do it in several steps. And if you do everything in once, step after each other, and then at the end want to make it, switch it on. And if you discover there are problems, the effort to locate and fix these problems, to find the cause, it's much more than if you do it in steps. Therefore, the basic rule is install a stage, check the correct function, required performance, and then start with the next one. But of course, the reality says economical pressure is high, less testing means lower costs. Really? I have to say it, really, because I'm from a test tool manufacturer. But anyhow, we also have the situation that subcontractors, installer are used, and it requires from the operator point of view some control if the installer does everything correct. And of course, the installer wants to show I did everything correct, and it normally shows it with a acceptance protocol or installation protocol. So both need somewhere kind of testing and to make sure that the network installation at the end is error-free. And the operator who really finds here the best compromise and balance between testing and not testing will have a big advantage. So it's a philosophy. How much testing, where is it needed, what type of test procedures. Most of the time it should be very simple, as the installer is not that they have always with high experts of testing. So this is my story about turn-up testing and troubleshooting. Now let's see how could be such a compromise, where we have to focus on. First, what is new in the 5G world? Okay, we learned about these 3 typical services. This is the user plane. Then we have the control plane. Of course, this is also a service required to that network, very reliable because it's managing all the devices. And we have the synchronization plane. And we learned it will probably be only in the mid-haul fronthaul area. Only when we have TSN, then it goes to the backhaul area when we have their TSN. But this is also something what we have to do. These are the performance requirements for 5G installation. So finally, it can be a wide spectrum of possible implementations. And again, this is fronthaul mid-haul area. These are different functional splits, aggregation, backhaul. And somewhere we organize it in layer 2 or layer 3 structure. And main transport technique, it will be Ethernet, maybe OTN, but main focus is Ethernet. And here at that area, you can already calculate how much capacity bandwidth is required to support the situation. For example, this situation, much more radio units, and therefore much more bandwidth here required. It's closely to 100 gig. Here maybe 10 gig, 25, 50 gig. And then here, you easily will come to 400 gig and more. 100 gig, 200 gig, 400 gig. These are new interfaces. And also a technology, FlexE, flexible Ethernet. So it's using n times 100 gig or n times 50 gig physicals. So which is n time means you can have 5, 6, 7, 800 gigabit capacity as a logical interface here. So this new technology, but it's already used, so it's available and can be part of the design of such a backhaul. Optics used there when you have these interfaces. So I listed it here because the SATA and SATA optics quite challenging. And if time-sensitive network, okay, we need here synchronization and therefore PTP implementation and verification. Okay, here are a list of further possible functions. I will not go through all of them, which is basic things: CR, CPS, committed information rate services, normal quality of service, higher capacity, very fast protection mechanism, maybe OEM function, operation optimization, maintenance, network function virtualization will be extremely used in 5G world in the Fronthaul mid-haul area. So a lot of things can come. So really a wide range, a wide spectrum of possible implementations. And when it comes to testing, such a test solution, yeah, we need to have the right range of test interfaces in our test tool, probably all of them, to simulate the right network load, to verify the specified SLAs. So yeah, 1 gig to 400 gig, 50 gig, 100 gig flexi physicals. This is typically a requirement for such a test tool. It should support it. Very high accurate delay measurements, round trip and one-way delay. Ready to support all these different optic types, especially ZR and ZR+. So we've learned ZR+ really is very high power consumption, and this means also very enhanced cooling to keep it cool enough. Portable with long battery lifetime, so 1 hour should be, more than 1 hour should easily be possible. And with some tricks, with our units, we can even do 2, 3, 4 hours if you want to. Then this typical service test, standard test, Y.1564, RFC 2544, RFC 6349, or long-term test. I will add a few words on that later on. And qualification of the physical link for this RS-FEC status becomes important. Optic self-test, OTDR modules also supported, fiber microscope power meter, and a cloud-based solution to do a workflow management when you have a wide rollout of new sites, remote coaching, and virtualization. Okay, wide spectrum of test features. And manual test, this is a state-of-the-art test. The RFC 2544, a wide, very old test specification. In the meantime, everywhere used in transport testing, transport verification, and I recommend to use only and do only throughput and round-trip testing, and also add a long-term test. We have the Viavi enhanced, it can do a lot of other things. It's not only the old RSC, it's now a really enhanced state-of-the-art RSC. The Y1564 is for multiple services. If you have on one physical interface more services established there, then you need to verify all the services. This is the 1564 spec. And if you want to go to the TCP level, there's a methodology, RFC 6349, to verify services based from the TCP end-to-end point of view. So TCP efficiency, TCP buffer delay. Okay, then, oh, sorry, I made one mistake, 27. So I will skip this slide, you will have it later on in your presentation because of the time. Troubleshooting now on 100 gig. My picture here shows I have a level 1 situation. This is my local link where I have all my physical errors. And I have here a layer 2 level when I have Ethernet frames, loss, frame check sequence errors. This is if the error is more behind the muxponder or the switcher router here. And if you focus on here, then we have to check first the optical level. 100 gig, we have these 4 lambdas, if they're all in the correct range. We have to check the frequency, if there is not too big offset. We have to check this RS-FEC performance. RS-FEC is a mechanism that a sender can add to its signal sent out information for the receiver that the receiver can find, can detect errors and correct them. Forward error correction. So we have then correctable error, and we have a correctable error rate. So this is the important part. We need to know where is our correctable error rate. Is it already very high? Then we risk that with a few changes, maybe a little bit more temperature, then this device, this optic plugged into this device will generate uncorrectable errors. And this is now disturbing the service. Monitors queuing, so this virtual lanes in just a 100 gig interface needs to be aligned in time, so no big difference in the delay in these different virtual lanes. we have to check the physical errors, and we have to correlate the physical errors and the protocol errors in time. So with a histogram form to really say, okay, problem is more here or problem is more here on a local link. And I typically prepare with our test tools, I call it a custom result page, where I summary up the most important results. This is the optical level received, how much I'm transmitting, how much I'm receiving, what is my error ratio rate, what is my correctable rate, what is my uncorrectable rate, to be sure that this interface now is correct and safe. I'm ready for operation to be connected to the real system port. If I do the same on 400 gig, there's a new factor coming. So this forward correction on 100 gig is recommended. It's not mandatory. It's recommended for the different interface types. If you, for example, use an optic with multimode fibers. But on the 400 gig, it's mandatory. It has to be used. And it's a very strong, it's called KP4 RS-FEC. It's a very strong algorithm to detect and correct errors. And this is why we need to to check and control this RS-FEC performance. And you see here, it's a A and B forward error correction function, and I have here the summary, and you see here the correctable error bitrate. It's quite good. And the other thing is what you have to check. This forward error correction is working with a block of symbols, 15 symbols in one block, and it can detect these errors in these symbols and correct them. And here in my example, these are this number of symbols, 1 to 15. There are 3 more. And if there's always per block only one symbol errored, really no problem. But in case there are more symbols errored, and if you have more symbols errored in the range of 3, 4, 5, then when we install the network, maybe connect to the other system board with a 400 gig optic, we risk to run in more errors in more symbols. And if we have more than 15 symbols errored, we have an uncorrectable situation. This means a bit error in the service level. So this is a bad situation. And this you have to qualify before you interconnect. So first qualify your optic, which you will later on use in the local system. Test it in the tester. What is the distribution? Is it good or is it bad? If it is good, okay, take the other one, check it, make the connection, check what you receive, and if it's still in a good range, okay, you can bring it in operation. And probably you have to do it from A to B and from B to A, so your local connection. It sounds a lot of work, but the experience is that this can happen. We have, Viavi has a division which is manufacturing lab tools for manufacturing of optics and for system manufacturers, and they have a lot of experience. And they told us, yes, if it's 3, 4, 5 symbols errored, you should already take care and look that you can improve this. And our portable test tool is the Viavi 1A1000, ONA1000, and yeah, we call it, there's a clean electrical signal preparation. So it's internally, it's introducing more or less no error to be able to qualify plugged in optics or to qualify connected links. And you can, of course, set thresholds when you won't get an alarm. If the error ratio rate of the correctable errors is above the threshold, this is all possible. Okay, this is about testing. I focused on these forward error correction parts because this is the most important thing. If this is working fine, probably the service, the Ethernet service is also working fine. Of course, we can generate here 400 gig 100% without any problem. But this is normal stuff. This is what we know since years, a lot of years. So with this new interfaces coming, we should focus on this. Therefore, I added it to this short presentation. One of the last slides is this fiber inspection. I only want to mention that you really take care. If you have a 400 gig with 4 lambdas inside, each is carrying 100 gig, and you don't take care on the optical connector, you will, with this a little bit dust on the connector like this, you will make for this forward error correction a very hard life, because it has to correct much more errors than in case the connector is clean. Okay, about the portfolio from Viavi. So this is only portfolio in the transport testing area. And if it's backhaul, easily you have 100 gigs. So this is our MTS 5800, 100 gig. It supports up to 2 times completely independent 100 gig ports, with OTN even 2 independent 112 gig ports. You can have the same fixed installed as a rack mount unit. And if it comes to 400 gig, we have our new ONA 1000. It supports the 400 gig Ethernet to turn up this. And let's say these are the two protocols, the two products we recommend if you have to install backhaul with 100 gig, or it's up to 400 gig. And these are smaller units, single port units, up to 10 gig. And PTP measurements, Sync E Wonder measurements, capture function, all this transport testing, Flex E, all what I mentioned in my presentation is possible with this unit up to 100 gig. And here we have our 400 gig on top. So I'm at the end. We're coming to the questions. So Q&A is open. Now I should, I guess from Richard, if there are some questions to answer.
Mm-hmm. Yes, we've had quite a few. Just for a quick bit of kind of checking before we go any further, we have had a question about asking whether it's possible to look back at this webinar later on. You'll actually be sent a download link for a copy so you can watch this back later on. We'll share the recording and so forth at that point, so we can do that then. Our first question is about the layers that are being seen on the backhaul. So layers 0, 1, 2 are you seeing on the backhaul, since Ethernet could be a layer 2 VPN. If Ethernet at layers 0 and 1, what standards of Ethernet are being used at that point?
So in the backhaul, if I started correct, so it's typically Ethernet. This is a layer 2 technology. And layer 1 is more or less than the fiber, DWDM, or in the Ethernet, it can be this Flex E. So Flex E is actually a layer 1 interface, a layer 1 transport technology. And I'm not sure if this answers the question. So yeah, layer 2 is virtual LAN, and layer 3 it's down to MPLS, can be MPLS. So, but on this high bandwidth requirements, so this Flex E with a kernelity of 5G will become their layer 1 interconnection interface. Hope it answers the question.
Timing appears to be critical for 5G and tends to be GPS derived, as we've seen. The north coast of Scotland has regular NATO military exercises, including GPS spoofing and denial operations. Will this in turn impact 5G in that region while these are going on?
Of course, if I understood it correct, so when you have this jammers or something which disturbs GPS receiver, and you have this, just let me show it. I have here a GPS receiver, and if it's disturbed by any attacks, then of course you miss here and lose here accuracy. So you will have then, if nothing is available, you have to go and hold over. Depending on oscillator, you will introduce here then a drift, and this can at the end mean that you have an extreme degradation of performance. So,
and on a similar subject, what's the acceptable time error for PTP at this point on a network?
The time error for PTP?
Yes.
Yeah. So let me go to the slide. Which one is it? Okay, this is this time error, and this is the overall time error. It's 1.1 microseconds. So this is here at this interface to the big reference, which is then the GNSS system. It should be less than 1.1 microsecond. This is the time error.
Yeah, lovely. And you refer to a packet-based network for transport. On the other hand, do you expect anyone to be using things like OTN, for example?
Yeah. Okay, OTN is then more really in the core, and OTN, OTU3, OTU4, and you map into the payload of OTN then the Ethernet part. So it's kind of in between layer 1 transport technique to structure more the backbone and the pipes through the backbone. You do it with OTN. So maybe you have, quickly look for the slide. Yeah. Like here, maybe you can here organize this with OTN, that you say here, okay, I have here now 2 big pipes to forward through the network, and you do it with OTN. Instead with Ethernet, instead with FlexE, you can do it with OTN. So this is, OTN is in the big carriers operators used, and it can be enhanced. Yeah, like we have FlexE, there is also kind of FlexO technology that you can N times OTU4. OTU4 means a capacity of 100 gig Ethernet per OTU4, so you can do it N times. So OTN will also be used, of course. Depends on the operator itself, if they go with OTN or not.
Okay, lovely. Are you aware of any 5G applications on smart grids already?
I think this is this Internet of Things. So once with smart grid, so you have your meter at home, which measures how much of power you are using, and this is then reported via 5G. So this is smart grid. If it's smart grid itself is PTP things, okay, then it's a separate thing. But 5G is then, I guess, used to collect data, to have maybe the sensors, to have these meters and collect this data. Because with 5G, you can reach every corner where you have no access with a cable or with a fixed wired network.
Okay. We've had another one on the time error question.
Yeah.
Would the same maximum time error be allowed in the case of the DSS based on 5G on bands below 3 gigahertz?
This is now not sure. So, and I can't answer this for the moment. And it's a mixture. The CSS is a mixture, and so it still requires, when you have then, let's say this way, I think the answer is when we have this TDD, just let me look for the slide. 12, this one, as soon as I have TD as an RF radio technology, you need time synchronization. So, and if it's in parallel FTD, not sure if it's used there in parallel, then of course it's only frequency needed. So as soon as I have TDD on the radio technology, on the RF side, you need time synchronization with this accuracy.
Okay.
So I'm not the real RF guy. So I know DSS is dynamic spectrum sharing, and if you have one spectrum for LTE, let's say it can be FTD, the other spectrum is then used for 5G with TDD, then you have to take care on that. Your frequency spectrum organization has to be correct. So, but I'm not the RS guy. I'm more the transport guy.
Okay, I think we've got time for one last question. Is there any, are you aware of any more upcoming, more stringent time synchronization standards for 5G above what we already have?
At the moment for me it's this 1.1 for the transport network, but I've heard it can go down to 500 or even less. It really depends what the services are requirement. And we have to see. At the moment, this is the requirement, and 5G is at the beginning. So, and we do not yet support this very tough beamforming carrier aggregation over multiple radio units. If this is coming, I assume, again, I'm not an RF guy, but I assume that the requirements for time sync will become more smaller or more tough. I'm sure.
Okay, wonderful.
According to my opinion, let's say.
Oh, no, absolutely. Right, well, at that point, I'd just like to say thank you to Roland for that very interesting look at this subject, and thank you all for attending. I trust that you found this informative and useful. Any questions that we haven't answered so far, I will share them with Roland, and we will attempt to come back to you as soon as possible with a complete answer. Please remember that all of the technologies and products that have been shown here can be rented through Electro Rent or put onto one of our financial solutions. So if you have any equipment needs going forward, please feel free to contact our sales team to discuss your requirements. If there are any questions that you haven't had time to put in today, or you feel we're not fully covered, please feel free to contact us to ask, and working with Viavi and ourselves will endeavour to get them answered for you. I hope you have a good rest of your day and week, and look forward to seeing you at the next one of our events. Thank you very much for your time.
Okay, thank you for listening. Bye.